We've already seen how when we look at large scale, the universe is dominated by dark matter, and that essentially we expect the universe to look pretty much like this and to reveal this dark matter skeleton. We also expect that this is essentially the backbone of the universe and that all these nodes, they are the locations that will allow galaxies to essentially form and evolve. However, we've already seen actually that if we just take a universe made of dark matter and we assume that every node of dark matter or every halo is a galaxy, and we actually use that to predict how the galaxy luminosity function will look like, we would actually be predicting this red line. However, observations show something very different. Observations are shown here where the number of faint galaxies is way below what would be predicted from dark matter only, and the same thing goes for the number of very luminous galaxies. Therefore, an important question that we need to ask is, what are we missing? Can we actually explain the discrepancy at both low luminosities and high luminosities? Now, it turns out that the explanation for this big difference has to do with some physical processes that have to do with baryons, not with dark matter. These processes are in general called feedback, so they are feedback processes, and they're actually very different, but they involve the release of energy, which means that not all dark matter halos will technically be a galaxy with the same scaling. In practice, what we think is happening is that at very low luminosities or low masses, low gravitational potential wells, then the explosions of supernova or supernova-driven winds can actually lead to velocities that exceed the escape velocity, and galaxies can actually kill themselves or essentially get rid of the gas that is no longer available to form stars. Therefore, it leads to a deficit of the number of galaxies. While at the luminous end, they're actually massive enough for supernova feedback to do very little, but in those galaxies, we know that supermassive black holes can actually have a very important role in regulating their evolution. Understanding feedback and how galaxies evolve really led to this model where galaxies are probably best seen as almost living creatures. In the simplest terms, what is happening is a galaxy will evolve essentially by getting inflows of gas that will be the fuel for new star formation. But whenever stars form, they will also form O and B stars that have short main sequence lifetimes and that very quickly go supernova, releasing tremendous amounts of energy. And we can see this in reality, for example, in this galaxy. This is a starburst galaxy where this effect is extremely strong. We can see these outflows driven by supernova winds. If you want to model it in a simple way, then a galaxy can probably look pretty much like this. You can think of it as a reservoir of, for example, long-lived stars. They're the ones that accumulate. And also, you have a reservoir of gas. Essentially, this gas can be converted to stars, but whenever that happens, on top of the long-lived stars, you also form short-lived stars. They're rare, but they will explode as supernova, and they will essentially lead to winds and outflows. Some of these outflows can actually exceed the escape velocity, and then the galaxy can lose the gas forever, or they can actually stay in a halo and actually come back to be part of the gas reservoir and then form more stars. The important thing to realize is that this gas reservoir will run out unless the galaxy keeps getting new gas inflows into the galaxy outside of the halo of the galaxy. And therefore, if you actually cut the galaxy from what we call the cosmic web, the fresh source of this gas inflow, then all the galaxy can do is keep forming stars with its own reservoir. But the problem is, for many galaxies, especially those that are low mass, whenever they form stars with this reservoir, they actually lead to supernova explosions that can lead to winds exceeding the escape velocity, meaning that after a while, the galaxy may not have any gas at all. We can probably see this even better with this illustration over here, and we can think of our own galaxy as something that actually satisfies these conditions. Our galaxy is massive enough so that when it forms stars and some supernova occur, sending essentially supernova-driven winds up, they are very hot, so we can actually see them in emission. At some point, because these winds will not exceed the escape velocity, they will actually start cooling, come down, and then become available to form more stars. You can think of this as some sort of fountain cycle. self-sustained star formation. There's always some gas that gets out of the galaxy, but not far enough, so it actually can cool and come back to the galaxy to form more stars. However, if you actually move this process to a galaxy that's much less massive than the Milky Way, then it's actually not that hard for this condition to happen. So the velocity of the outflows can very easily exceed the escape velocity that you can calculate, and this will of course depend on the exact position within the galaxy, this radius that you're using, meaning that it's easier to actually extract gas from the edges of a galaxy than it is from their core, of course. But what this means is that if a galaxy is forming stars and this condition is fulfilled for a long time, then all the galaxy is doing is really getting rid of its own gas. And at some point, there will be no more gas to form stars, and the galaxy will quench or essentially die. It will stop forming stars, and all that will happen is those stars will just evolve. And after a while, we'll no longer see some of the most massive spectral types because they would have evolved away and gone supernova, for example. As we'll see in section 15, then modeling these processes in real conditions and actually being very hands-off reveals an amazing picture of how galaxies form and evolve. And we can have a look, and you can see here a galaxy like the Milky Way evolving in terms of its stellar components on the left and its gas components on the right. And the colors, the different colors on the right, show you the different phases of the gas, such as the hottest gas, which is red, and the coldest gas, that is pink. And what we're seeing is essentially the effects of the release of energy through supernova winds and the process of feedback. And what we've learned over the last few years is that this feedback process in galaxies like the Milky Way leads to self-regulation. By understanding feedback from massive stars and supernova, we now understand some fundamental observations that have been done over the last 10 to 20 years. And these observations are essentially illustrated here. In our universe, the ratio between the amount of stars that a galaxy was able to form and its dark matter halo actually goes up when you go from dark matter halos of around 10 to the 10 solar masses to about 10 to the 12 solar masses. This is the mass of our Milky Way's halo. What these observations are telling us is that galaxies with a dark matter halo around the same mass as the Milky Way are the most efficient at converting gas into stars. What happens is if you go to dark matter halos which are lower mass, where the gravitational potential wells are not as strong, then actually those galaxies are very inefficient at converting stars. We're talking about something like less than 1%. And it's also important to point out that even though galaxies like the Milky Way are the most efficient, we're still way below sort of 10%. So they're definitely not very efficient systems. However, what we now understand is that the reason why these galaxies are so inefficient at converting gas into stars is because of supernova-driven winds. Essentially, these galaxies are not massive enough to actually keep the gas whenever they form too many stars. And therefore, you need to move to galaxies like pretty much the Milky Way so that the escape velocity is so high that even some of the strongest supernova winds do not exceed it, at least typically. And therefore, a galaxy can just keep renovating its own gas with the fountain mode and actually transform most of its gas into stars instead of just wasting it and throwing it away. Of course, a really interesting result is that once you go to even more massive galaxies, actually this efficiency keeps going down and down and down, such that when you look at the most massive halos, actually they tend to host clusters of galaxies. They become incredibly inefficient. But this is not because of supernova-driven winds, because here, I mean, things are so massive that there's no way that supernova can drive winds to exceed escape velocity, but it's due to something else that becomes much more important at high masses, which have to do with the activity of AGN, or active galactic nuclei. And therefore, we can now interpret this fundamental result of the efficiency of galaxies over the entire universe, essentially as being driven by stellar feedback at the low masses and by something else at high masses that we'll see is driven by the activity of supermassive black holes at the centers of galaxies.